Greetings, I offer you this session on algorithms and problem solving. An algorithm is simply a set of instructions that enable you to solve particular things repetitively. And problem solving lies at the heart of what a mathematician is really good at. So hopefully by the end of this session you will have a better feel for what goes into being a mathematician and makes mathematics work the way it does. So we've got some basic algorithms that you are well used to. So for example, if I'm doing something like, if I can get it to work, 167 and subtracting 89 from that, then you have the decomposition algorithm that says I can't do 7, I can't take 9 from 7, so I'll decompose this down to 5 and make that 50 and 17. And 17 take away 9 will give me 8, no real problem. And I've got 5, I've got to take 8 away from it, I can't do that, I'll make that a 0, make that 15, and hence I get 78, no problems. I think I'm quite comfortable that I've got that correct, no guarantee though. What number of you may not actually realise that there is a slightly different algorithm for this, and that if you start at 89 and you use jumping techniques, so you say, right, I'm going to go up 1 to take me to 90, from 90 to 160, I can do easily as another 70, to 167 my target is another 7, and I've got 1 plus 70 plus 7 is 78, gives me the same thing again, slightly different way of doing the same thing. With regard to multiplication, if I wanted to do, let's say, 325 multiplied by 67, most of you being bright, intelligent young human beings could probably manage the standard algorithm where you go through and you multiply by 7, so 7 5s are 35, that's 5 down, 3 carried. 7 2s are 14 plus the 3 gives me 17, 1 carried, 7 3s 21, 22. And then what happens most frequently is people forget that that 6 actually represents a 60, so they forget to put the 0. Some people just put a space in there. 6 5s are 30, of course, so I've got 3 carried. 6 2s are 12 plus the 3 gives me 15. Helps to get it in the right place. 1 carried. 6 3s are 18 plus the 1 gives me 19. So I've got 5 7 7 11 2 1 7 7 5. Haven't checked that one, but some of you may know the box algorithm for this, where, and this is in effect chunking it, so you split it into 300, 20 and 5, into 60 and 7. So I've got 18000 there, 1200 there, 300 here, 35, 140, 2100, and I've got to add that lot up, which is a bit of a pain. What a number of you possibly haven't come across is a Napier algorithm for it, after the Scots mathematician John Napier, and he approaches it in quite a different way. And so this is a Napier grid. Helps if your lines are straight, and the algorithm is relatively straightforward. You stick your numbers in, 3 2 5 6 7. Some people like to put a multiplication in the corner, Flossie in the corner there, help if my lines were straight, and you simply do your multiplications as normal. So bottom right corner is 7 horizontally, 5 vertically, so 35. So you put your tens in the top part of the box, your units in the bottom part of the box. Work your ways along. 7 2s are 14, so that's 1 10 and a 4. 7 3s are 21. 6 5s are 30, so I'll put a 0 in there, although I don't have to. 6 2s are 12. 6 3s are 18. So your tables, which you learnt when you were a little person, are really, really useful. Now all you do is you just slide down the slopes. So in this particular slope, I've got a 5. In this slope going down here, I've got a 7, because nothing plus 4 plus 3 makes 7 last time I checked. Going down this slope here, 3 plus 2 gives me 5, plus another 2 gives me 7. Down this slope here, 2 and 8 gives me 10, plus the 1 gives me 11. And I'll carry that one over there. So 2, 1, 7, 7, 5. Oh, I'll get the same answer twice. That's always useful. Notice I didn't use this one because it's too much like hard work for me. Being a bearer of very little brain, I don't like to do hard sums, even though I'm supposed to be a mathematician. But that's quite an interesting one. The actual act of adding on diagonals, which is unusual, means that you actually automatically line up your units and tens and hundreds. Because if you think about it, when you were little, maybe you put us and tus and hers or in a degagant above your columns in order to give you that place values feeling. So a lot of the work that you've been doing early on in mathematics is a standard algorithm, but you've not seen them in algorithmic form. You've just been taught a method. So if you think of it, an algorithm is just a method for doing things. So completing the square. Now, this relies on the fact that if I square a bracket, oops, I didn't really want a red one there. So I'll take out my red and put black. It looks better, doesn't it? So I know that if I am expanding a binomial bracket, that means whatever I'm doing, I multiply by itself. And I always like being silly to make sure the distributive law of mathematics applies, and that I've got to multiply everything in one bracket by everything in the other. So I'll get x squared plus ax plus another ax plus a squared, which of course gives me x squared plus 2ax plus a squared. And I don't need to have done that, but it does. I always like to make sure that I get the distributive law going on, so therefore look at a smiley face and you've got it working. But the important thing is the connection between this term here, the x term, and what's in the bracket, the constant term, is it's always half. So if I wanted to use an algorithm for completing the square on a function, x squared, let's say minus 6x plus 10, then I simply need to halve that constant there, so half of minus 3 all squared. But that would give me an extra minus 3 squared, which we know is positive 9, which I don't want, so I've got the plus 10 that's loitering around already. Take 9 away from it. So x squared minus 6x plus 10 is the same as writing x minus 3 all squared plus 1. Now that tells me certain things. That the graph of this, I know it's because it's an x squared, it's going to be a happy parabola. It's got an intercept at 10, which I can tell from the original function, but it's got a least point at positive 1. So my graph is going to look like that, and its line of symmetry is the line x equals 3, because x minus 3 is equal to 0. So the idea of completing the square is to actually give you that indication there. Now, obviously, so my algorithm basically says halve your x coefficient and subtract the square of that result. You notice I'm not writing it down, I'm putting it verbally because it's a fairly simplistic one. So if I apply this to a slightly more difficult situation, x squared minus 5x plus 2, then half of minus 5 gives me minus 5 over 2 or minus 2.5, whichever you prefer. I've still got my plus 2 there because I haven't dealt with it yet. Now I've got to subtract the square of this 5 over 2. Now that's dead easy. You notice I wrote it as 5 over 2 rather than 2.5 or 2.5 because all I do is square the top, which gives me 25, square the bottom, which gives me 4. And 2 is 8 over 4 minus 25 over 4, so this becomes x minus 5 over 2 all squared minus 17 over 4, because 8 minus 25 is minus 17. And again, I could sketch that one. Its line of symmetry is x equals 2.5 or x equals 5 over 2. Its least point occurs at 5 over 2 minus 17 over 4. It's got an intercept at plus 2, so therefore it will have two roots, both on the positive x-axis. So I need to refine my algorithm slightly if I've got a constant outside on the x squared term. Now, all you do is you put an extra step in, you say, all right, you pull out a common factor 2. And then you apply the standard algorithm after that. So you say, okay, got lots of brackets now. Half of 3 over 2 is 3 over 4. I've got a minus 5 over 2. 3 over 4 is 9 over 16. He says writing 3 instead it should have been a 2. I can make sure I've got my brackets in there. Now, in order to subtract those two bits, minus 5 over 2 minus 9 over 16, I've got to have them both over 16. So if I make the 5 over 2 over 16, it's going to be minus 40. And I'll actually write that in. So 2 bracket, ooh, I've gone red. Didn't really mean to go red. I think I accidentally pressed the thing. 2 bracket bracket x minus 3 over 4 all squared minus 40 over 8. Behave yourself 40 over 16 minus 9 over 16. So this would actually be exactly the same as 2 bracket x minus 3 over 4 all squared. I've got minus 40 minus 9, which is minus 49 over 16, but then I'm going to multiply by 2, so minus 49 over 8. And that tells me where the line of symmetry is. X equals 3/4. It tells me that the least point is at 3/4 minus 49 over 8, which if you prefer is minus 6 1/8. And the 2 tells me it is quite steep. It's a change of gradient, but that's all it is. But it's a simple algorithm. It allows me to do certain things. Quick fortune telling one for you. I won't read this to you. You're quite capable of reading it on your own. So I like to think that perhaps that fits, and you'll perhaps understand why a little bit later on. But this leads us to Zolas' algorithm, which will tell you, providing you were born in the time when we have the Gregorian calendar in place, which is anything after about 1680, what day of the week you were born on. So it's not a particularly difficult algorithm. It introduces a couple of different things that you need to be aware of. And we'll have a play with it. But it's there for you to have a look at. So we've got these things called floor functions and modulo maths. Now a floor function is quite an interesting function because you'll frequently see it as the int part of something. And the int part means it is only the integer part. You apply your standard rounding stratagem. Your standard rounding stratagem is that if it's more than half or more, you go up. But in fact, so if I want the floor part, it makes a very strange graph, because anything between 0 and 1 comes out as 0. Anything between 1 and 2 comes out as 1. Anything between 1 and 3 comes out as 2. Anything between 3 and 4. Now, that leads to a rather strange situation, because if my value is between 0 and -1, then we can't go to our traditional thing. In fact, it turns out, because we've already got a 0 there, so this one would be int 0 point something, anything between 0 and -1. And so what we've got is that anything between actually int to -1 under the floor function, which is a little bit strange, but you will find that we're only interested in the whole number parts. So if you think about it, it's only the whole number parts. And modulo maths is remainder mathematics. So if I'm in sort of modulo 4, I'm interested in, it only gives a remainder, so the only numbers I would have available are 0, 1, 2, and 3. So if I did 2 plus 3 mod 4, well, 2 plus 3 should be 5, but if I divide that by 4, I get once remainder 1, so therefore I get a rather strange situation that if I'm in mod 4, I get an answer of 1. So it's a remainder technique, and it looks at just those remainders. Now, we're working in mod 7 maths in Zolas algorithm because there are 7 days in a week. And it may be interesting to realize that the Gregorian calendar was set by Pope Gregory. So it's a Christian church enactment, hence we have 12 months of the year for Christianity purposes. But it encompasses the number 7, which was a very important number in Norse mythology. And you'll find that Christian systems also encompass important numbers from other religions. So interesting ideas going on. But modulo maths, you'll see more of it in. Now, I can remember this date, 20th of the 10th, 1986, because it was the day on which our first child was actually born. I can remember there was 11:15 in the morning on the 20th of the 10th, 1986. I'd been into school and been called back, and so I got into school, met the students that were due to start that day on their teaching practice, and promptly left. But I can remember holding our son for the first time at 11:15 in the morning on that particular day. So I know well what day it is, but I'm going to use it to show how to work Zolas algorithm. So what I've got in this particular case is that D is 20, M is 10, and Y is 1986. And so M is not 1 or 2 in this particular case, so I can ignore that particular thing. So C is going to be the first 2 digits of the year, 1919, and K is going to be 86. And this is where my floor function comes in. So we're not going to dwell too much on why it's 2.6m and 5.39. So I need to do 2.6 times 10 minus 5.39, and I can do 2.6 times 10, that's 26, minus 5.39, no real problem, 20.61. But I only want the integer part of that, so I don't round up. I'm going to use the 20. This is where my floor function comes in, the whole number part of it. K over 4. K over 4. So I've got 86 divided by 4. Well, 4's into 86 go 21.5 times. 4's into 8 go twice, into 6 go 1.5, so 21.5. I want the integer part of that, so it's 21. C over 4 is going to be 19 over 4, which is 4.75, so that's just 4. And then I add D and K. Well, D was 20, K was 86, and so I need to subtract 2C, so I suppose it might make sense for me to add this lot up. 6 and 4 gives me 10, plus 1 gives me 11. Okay, don't forget my carryover, standard algorithm, being well taught me. 8 and 2 gives me 10 plus 11, 12, 13, 14, 15, 1, 5, 1. I'm going to subtract 2C from it. Well, 2C is going to be 38. 151 minus 38 is 113. And this is where I need to do my modulo maths. I find the remainder when it's divided by 7, so I need to do 7s into 113. Okay, no real problem there. It'll go in 16 times, so 7s into 1 don't go into, 11 go once, 4 remaining. Okay, and into 43 goes 6 times, remainder 1. You might remember doing subdivisions like that, so you actually do know what modular things is, but my remainder is 1. Okay, so therefore my son, who's now, or our son, is Monday, of course, dydd Llun. And it was indeed a Monday morning a long, long time ago. And of course, being slightly biased, so therefore David is fairer face. And I claim that I was born on a Monday as well, but I'm not going to check it out or show you that because that was a very long time ago. But it still was within the Gregorian calendar. But there's some interesting things going on in there. It works. And if you think about how difficult it is to work with the fact that we have leap years, we have months in which there are different numbers of days, that's quite an interesting piece of work. Now, we get into problem solving. So I've done a little bit on algorithms there. And we're now into a little bit of work on problem solving. I may not do all of this, but I might just flick through some that will leave you some to think on. We can't teach you everything there is to know in the world. You think about how things are changing, the pace at which they're changing, the way that modern technology has affected our lives. Things that I taught about as theoretical possibilities are now everyday realities. And I've been teaching, I've been teaching for a long time, but what was theory has become reality. And what is your potential developments will become reality in your lifetime. So But the skill of a mathematician is that ability to take information and make it work, draw a conclusion from it and develop it. So Hypatia, who was the first female or first acknowledged female mathematician, who met a very, very grisly end. If you want to know about Hypatia, look her up on Google, but she upset the Christians, and that was not a good thing to do. But one of her things is reserve your right to think, for even to think wrongly is better than not to think at all. You actually learn as much from your mistakes as you do from your successes. Whilst it's nice to get a whole row of ticks, you'll learn more about yourself and mathematics by getting the odd thing wrong and working out why it's wrong. I say, you may know of a standard material called WD-40, water dispersant 40. It's great for freeing seized up things in cars and things like that and dispersing water. The reason it's called WD-40 is it was the 40th attempt to get it right. You've got to get things wrong to get things right. So we need to be able to solve problems, and one of the things with solving problems is really to make it simple. Don't complicate things. One of the things that we know is that in a standard football team, I've got 11 players, but I've only got 7 days of the week. And if the situation were that there were no 2 players born on any one day of the week, I could only possibly have 1 times 7, which gives me 7. But seeing as I need 11 players, 11 suggests that at least 2 of them, or several of them, a number of them, maybe 2, 3, 4, have got to be born on the same day of the week. There's got to be duplications, otherwise I can't have 11 players in my football team. And of course, if you go to extend it to your reserves, 2 or 3 reserves for a game, then they may not be born, they may not have the same birthday, but they are born on the same day of the week. And if you link back to Zolas' algorithm, you can check it. So solving problems helps mathematicians. They're about logic and reasoning, and mathematicians are really well sought after in university terms. The big companies come round to the top universities for mathematics, and they seek out the best of the mathematicians because those are the people who can solve the problems for the future. And they may not be mathematical problems. I don't sit in my office in the university when I'm there solving hard sums. I only ever solve easy ones because I don't like hard sums. They hurt my brain. So you need to make things simple in order to solve them. So the situation is, it's dead easy to prove verbally that there are going to be 2 players born on the same day of the week, because otherwise you can't have more than 7 players in your team. Simple. But a lot of people would find that much more difficult to work out. So, question for you here is, can you place 215 items in 20 boxes so there's a different number of items in each box? Well, the simplest situation is to say, all right, I want 1 plus 2 plus 3 plus 4, so I've got to have a number of different things, plus 5 plus ellipsis, which means on, up to 20. And I need to know what that is. Now, this brings us into the realm of Gaussian mathematics and Carl Friedrich Gauss, who's a phenomenally interesting person. Story has it that Gauss was very, very bright at mathematics, was able to do an awful lot of things very well, and was upsetting his teacher because he was actually better than his teacher. Now, my aim as a mathematician, as a teacher myself, is always to develop the thinking of the people so that they're better ultimately than me. The only difference between them and me is that I do it every day, therefore I'm more practiced. But Gauss was meant to be a phenomenon, and in fact Gauss is acknowledged to be the first amongst mathematicians. So without Gauss, a lot of our mathematics wouldn't exist. And the story has it that Gauss was told to add together all the numbers from 1 to 1,000, and in doing so was able to solve that very, very quickly. And he used quite an easy strategy. If you take the first number in your system and your last number, then 20 plus 1 gives us 21. If you take the second number and the second to last, which was 19, 2 plus 19 also gives me 21. So if I pair up my numbers, I'll get 21 each time. Well, if I've got 20 numbers, how many pairs have I got? So I've got 20 pairs of 21. But I haven't got 20 pairs. I've only got half that, 10 pairs of 21. So that means that if I wanted to do the sum between r equals 1 and 20 of the r's, which means 1 plus 2 plus 3 plus that's got to be equal to 210. But I've got 215 items. If I wanted to have a different number in each box, then I could only have 210 because I've got a remainder of 5. And if I've got to put them in boxes, they'll have to go into boxes so that there are more, perhaps, numbers in certain boxes. If I've only got 20 boxes and I've got to put them in, then unless I load up the top ones, so I have, unless I load up the top ones so that they've got different numbers in, but if the capacity of a box is 20, I'm scuppered. They'd have to go in the bottom ones, in which case I'd get some duplication. So the answer is probably can't. You have to think it through. But Gauss is an important person to look up sometime. It's a good one for you to think through. I'm not going to actually go through it now because I'm looking at the time. Midpoints of adjacent sides of a square are joined to make a smaller square inside the original larger one. How many times smaller is the area of the small square than the larger one? It's a problem. It's a problem that does occur. But it only needs a simple solution. Easiest way to do it, and I'll start you off, but I'm not going any further, is to start off with a square of side 2. Don't make things difficult, make things simple. Once you've got that, you can do something with it. This factorial notation, which the Americans call shriek, n-shriek. My American accent is appalling, never mind. Now, this requires you to do a little bit of thinking. So 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1, etc., etc., etc. But this requires a bit of an exhaustive approach, but think it through. Don't make it difficult. The answer, even though it's a problem, is not difficult. There is a saying that says there are no such things as problems, only solutions that we have yet to find. And your challenge is to find the solution.